Okay, so welcome to class today. There was a question up here about the test. The first test is 2 weeks from today, and I will go over we'll have a 15 to 20 minute review session as part of class next week. So we'll probably do that at the end of the lecture, like before the lab. The week of the test, I'll be in Hattiesburg, but I'll only be here for the first hour of the exam. And then Chris will proctor the remaining hour of the exam. Down on the coast, Corey will proctor the entire exam. He would have either way, because I'm not down there. But so we'll go over both the content, the format, and have a review session next week. I've taught this class several times, so I'll modify the test, and I should even have a copy of the test from which I'll base the review session on. So but we'll do that next week. So if there's any general questions about the test, you're welcome to ask them, but we will have a time specifically for asking questions about the test. Does that make sense? Okay. Thought I had it open already. Oh, there it is. Okay, so we're on the third week of meetings for this class. It's going by quick. After today, we'll be 3 weeks in. Today we're going to talk about geographic data. Now, I asked this before, and I think I got a response that was about half of the people in the course are also in Vandana's 217 course. But I want to ask again, because this time it's a little different question, because that time it was about the final exams conflicting. But who here is either concurrently enrolled in 217 or has taken 217 before? All right, it's still about the same number. It doesn't look like there's too many that are in the category of just taken it before. All right, well, good. This is really kind of the last week where there'll be some overlap. There'll be less overlap this week than there was last week when we talked about map projections. That is a topic that really needs to be discussed in both courses. Today, we're going to talk about a topic that gets discussed in both courses, but we're really going to come at it from a cartography perspective rather than from just general data. Okay, but you do need to understand geographic data in order to symbolize it, and that's what today is going to be about. And what do I mean by symbolize it? I'll open up ArcGIS here real quick. Okay. You don't have to do this as part of the lecture. Just follow along. If you want to, you can, but I don't think I put the data. I didn't put the data up there for all you that I'm going to demonstrate here. So I'm just going to make some basic map here, and I have ArcGIS. I'm going to connect to my C drive because the data is on my C drive. I just put some USA data here. So I'm going to add, let's just add the interstates and the state boundaries. I'm going to add those two in here. All right. Now, you may not be experts at this yet, but if you just look at this map, it's kind of the same question that we had last week. Is it, but maybe it's a little easier to tell now. Is that what coordinate system do you think is being shown? And I think that was the answer last week. So Still not right. Somebody said UTM. That's great. Thanks for speaking up. So UTM is a coordinate system that really is only for small slivers of the Earth. Okay. So I did this last week. Let's say that we want to change this to a UTM coordinate system. Go to UTM here, and I'm going to choose the UTM system for that would be good for around here. Okay. It's going to look like, well, that's actually not. That's not even it. But should have picked a different one. Ah, there we go. So it looks okay for a little portion of the United States, but it's still shaped a little weird. Remember, with the UTM coordinate system, it's designed to show narrow slivers of the Earth, and anything outside of it's actually coming down about right here, the center of the UTM zone. Anything outside of that zone is fairly well distorted, especially as you move this way outside of the UTM zone. You can see there's more distortion here. This side is much wider than it should be. Alaska gets so distorted that it doesn't even show up on the map. Okay. So by default, this coordinate system that came up was a geographic coordinate system, and it was just world WGS 84. Okay. So that's what the data is in. So one of the reasons that I can tell this, again, is that the coordinate system down here in the lower right-hand corner, coordinate system is reported in decimal degrees. So the units are decimal degrees. So the decimal degrees have been plotted as X and Y data. So you know right off that if the units that have been plotted as X and Y are really degrees, that you're in a geographic coordinate system. It's a geographic coordinate system, and it's really not important which one it is which datum are we using? Are we using WGS 84 or NAD 83? That doesn't matter. Okay, so that was just a review from last week. Let's say I want to make a map of just the United States. I'm not too concerned about Alaska. So one of the first things that I would do is choose an appropriate coordinate system for the entire United States. So I'm going to choose, there's got to be one in here, continental, North America, USA, or NAD 27, NAD 83, contiguous, USA, Albers. You can kind of tell from the kind of cryptic name that it is designed for the contiguous United States. And this Albers projection is it's a conformal projection, and so it tries to maintain a shape at the expense of the other parameters that we talked about last week. Okay, so I say OK here, and it's going to make Alaska a little bit worse, but I'm just concerned about the United States. Shouldn't have said that. I'm just concerned about the continental United States. So I zoom in there. I think most people would agree that that map looks more pleasing than it did when it was unprojected or it was in geographic coordinate systems. You'll hear people say both of those. Okay? A geographic coordinate system is unprojected data. So now it's been projected, and it looks better. The sides are. Okay, so today we are going to talk about geographic data. All right. Now, for those of you who are in a GIS class, or maybe those of you who just want to answer this question because you think you know the answer, what is geographic data?
Like a certain region using like the delta output and the delta how much data you usually find in the table.
Right. So you mentioned table. You mentioned spatial data. Okay. So I've pointed to the TV where I can see y'all from the coast. All right. Actually, both of those answers are good, and combined, they make a complete answer. Well, the datum is part of the spatial nature of the data. So, spatial data, or geographic data, or GIS data, the data that's in here, is composed of two parts. One part is all the coordinates that make up the spatial data. The other part is the tabular information, the table data that Sarah was talking about. And there's a link between them. They're like connected. And that's what makes it work inside of a GIS system. So if I right click on this guy, I'm sure you've done this if you're in the GIS class, say open attribute table. This is the data. We're not going to get much, we're not going to think about it much more beyond this in this class. In GIS class, you're going to drill down into that a little bit in more detail. But this is the data here, okay? This is the finest level that we need to think about the data for this course, okay? So we have rows and columns of data that we're showing here, okay? The rows represent entities, things out in the real world. And they can be ideas of things, like in most cases, can you actually see the boundary of a state in most cases? Right? No, you can't. I mean, sometimes you can, there's a sign that says welcome to Mississippi, feels like coming home or whatever. But if it wasn't for that sign, there's no like thing in the real world that actually represents that. It's defined by some governing body that made up that boundary. Right? On the other hand, what about these interstates? Those interstates exist in the real world? Yeah. So they exist in the real world. Now, each line here represents one of those things. So here we have, well, that's a bad example for me to select Hawaii. Here I've selected the row Washington. Washington is the state in the upper northwest of the United States of America. And you can see how it highlighted it in blue when I selected it on the map. Okay? So that entity's been selected. And to drive home this point, what do the columns represent? What do the columns represent in this table? Sorry, what was that? Longitude. The columns here. Is the state name a longitude or subregion? What are these things? What are these columns? So the rows represent entities, things in the real world. And what are these columns? Suppose what do they mean? Attributes. Yes. Yeah, they're attributes. They are just things that describe this row in the table. So Washington is a description of this row in the table. Okay? What sort of description? It tells us what the state name is. I go over here and look at POP 2000. It's kind of cryptic. What do you suppose POP 2000 might mean? Yes, the population of Washington in the year 2000. Okay? So we can read the value there that says it looks like 5,894,221. And then the population in 2005, it looks like it went up to 6,319,255. So we have attributes. And all of these are attributes. Some of them are of varying usefulness, but they're all attributes. So now we can look at, looks like there's a bunch of census data in here that's telling us about different age groups and how many there are, the average household size, all sorts of things. Okay. And we've got other things like the subregion. Subregion looks like Washington and Hawaii are in the same subregion, as is California down here. So we can have multiple entities with the same attribute. That's fine. They just have attributes. So those are rows and columns of information. The spatial information is actually stored as an attribute. In other words, the way that most GIS systems work is that they consider one of the attributes to be where it exists in space. So if somebody clicks on there, you're not going to be able to get the information. Okay, I can't get it in this way, but what is actually stored in there, it says polygon, but what's actually stored in there are the coordinates. Do this on here so that it shows up in the video. Are all these coordinates that go all the way around the state of Washington and describe the state of Washington. They're coordinates. Now, most GIS systems only allow you to store in the same layer objects of the same data type. And there are three basic data types. There are points, there are lines, and there are polygons. And really, everything boils down to points, though. Okay? Points are the fundamental unit here. So we can have just points. We can have things that are actually multiple points. Okay? That might be, I'll probably turn that down. I thought that that might be a little bit weird. What's something that could be multiple points? Maybe I'll come back to that in a second. But if you can think of a real world entity that actually be made up of multiple points, it is possible. All right. Then the next thing is lines, and lines are actually just a bunch of points. So these interstates are defined by points, but they're defined by a bunch of points, and then they're just connected. And then you can have polygons, and polygons are also just a bunch of points, but they started in with the same point, so they close the loop. Okay. All right, so we're going to talk a little bit about that. There is another type of GIS data, and that's called it's called raster data. This is called vector data. Okay, raster data are just basically images that don't always store image data. Okay? We're not going to get too into raster data in this class, but we'll get to it a little bit when we talk about surfaces. Okay? So I'll leave that until we talk about surfaces. So mostly we'll deal with this kind of data. So today we're going to talk about the shape data as well as the other attributes. And we're going to talk about getting that data into the system. We're going to talk about how all the considerations that you have to do to think about what is the data type. Because even at this point, you probably realize that this attribute, state name, is different than this attribute, top 2000. Right? There's some differences between those two columns. One's a number, and one is just a label. And there are different things you could do to symbolize those two types of attributes. But I'll show you what I mean by that. So I've got my states here. And in ArcGIS, the way I symbolize things is I go to symbology, and I can choose that I want to pick the state name as the symbol. And I hit apply. Add all values. Sorry, then hit apply. By the way, I want to not highlight Washington anymore. Selection, clear selection. All right, so now I have a map this map maybe looks similar to some map that you had hanging on your wall, not your own wall, but hanging on the wall in one of your classrooms in school. Okay, I'm sure there's a wall, something like that somewhere around here. The colors are random though. In real life, if I were to make a map, a good-looking map, I would make sure that there are, at least as few times as possible, colors that aren't right next to each other. It's hard to see that there's a difference between Nebraska and Wyoming here, or sorry, that's Colorado. Nebraska and Colorado because they're the same color. I can go down and edit that if I really wanted to. So let's, Wyoming. I want to change that to be, or sorry, Colorado is the one I want to change. You could just change it. That's probably not a good color to use either. All right, well, anyway, I can change the colors. And when I symbolize something like this, I'm using categorical data. In other words, they're just labels. However, if I want to symbolize them based on population, I've got some other options. So I can go down to quantities and choose population. Say, okay, now, what do the darker states in this map represent? Right, states with a greater population, okay? Now, there's all sorts of things to consider. What if I did this population 2000, but I chose a color ramp that looked like this and said, okay. Now is it a little bit harder to tell which ones have more population than the other? This color ramp is much better suited for the unique values classification, the one where we had every state be a different color. If I chose a similar color scheme, but change this back to state name. Okay. ArcGIS is smart enough to say, oh, you have categorical data, therefore I'm going to choose a color scheme that's more appropriate for categorical data. But you can still make a mistake, as you saw there. Right? Okay. Now another thing that I could do is I already said the states are polygons. What if I wanted to actually symbolize them as a different type of value? Maybe I wanted to use points. You can do that. Okay. Do something like this. I've got population 2000, and I'm symbolizing them as points. So in this case, what do the larger circles represent? So it's the same, more population. So those larger circles represent higher populations. And so as we go through the next few weeks, after this week, we're going to talk about different map types and different ways to symbolize things. So talking about data from a cartographic perspective means that we're thinking about how it gets symbolized, and it doesn't necessarily get symbolized using the same data structure that it's in to begin with. All right. At this point, I'm gonna do the lecture, and I might refer back to some of the concepts I talked about there. All right, so you should all have a copy of this if you want to go through it. All right. So let's just skip to the next one there. So I talked about this a little bit already. Okay. The real world has real world things in it. And in this slide, I'm calling that phenomenon. Okay. Real world phenomena. And we have to take the real world phenomena and turn it into data. Okay. And the first thing that we do, the first process that we undergo, is to think about real world things as objects that have attributes. Okay? So we can divide the world up. But here's an example. The city of Hattiesburg would be an object, and it could have a population associated with it. Okay? And its population would be an attribute or part of the data. The number of roads would be another attribute. The mayor might be an attribute. And there's literally an infinite number of attributes that we could come up with for the city of Hattiesburg. But as cartographers, if we're going to make a map, we need to know, or we need to determine which attributes we need to make our map. And also, the second thing is, we need to come up with the way that we're going to show or symbolize the object of the city of Hattiesburg if we're going to put it on a map. Okay? Anybody seen a map of Hattiesburg, what it actually looks like, the outline of Hattiesburg? You've probably all seen that. Okay? Looks kind of weird, but lots of cities do. That has boundaries that go out, way out on 98 and that sort of thing. But we could symbolize Hattiesburg as a polygon. Okay. Now, if we're showing a map of all of Mississippi, we may want to show Hattiesburg as just a point. If we're showing a map of the United States of America, we may not even want to show Hattiesburg, depending on what our map is depicting. Okay. All right. We observe phenomenon, but we map or display the data. All right. Now, when I'm talking about the spatial component of the data, when I'm talking about the decision of how to symbolize Hattiesburg or Gulfport or Long Beach or whatever, wherever we're talking about, the spatial component is one of these spatial dimensions. It's either a point, a line, an area, which is just another word for a polygon, but that's the diagram, or a volume. It can be a volume, or it can change through time. Okay. Maybe we should have a little divider through here. Points, lines, areas, volumes. Typically, when we're making a two-dimensional map, we have points, lines, and areas, and that's it. Okay? All right, so a point is considered zero-dimensional because it does not have area. A line is considered one-dimensional because it has length, but it doesn't have width. An area is considered two-dimensional. Of course, a volume is considered three-dimensional. Now, your data itself can be, this is what I just trying to show the example. You can have states, they can be areas. You can actually symbolize those states as just a point. Well, the point symbol being the size of that population base. Now, most lines, we actually assign a width to. We assign a width to those lines when we're doing cartography. We have a few considerations here. Okay, the spatial dimension is driven by available data. We may not have an area representation of the city of Hattiesburg, and it may not be necessary for the map we're creating. It can be dependent on scale. That's exactly what I was talking about. At some scales, it's very appropriate to map city boundaries. At a different scale, a scale that was showing the whole United States, it's probably more appropriate to show cities as points. Usually you can decrease the dimension of available data, but cannot increase. So that's what I was, all my examples were doing that. We can start with polygons and turn them into points. We can start with lines and turn them into points. But it's hard to take points and turn them into areas. because we don't have the representation. You have to go make that data. So here are some examples of things that you might symbolize as points, things that you might symbolize as lines, and things that you might symbolize as areas. This is also a slide from your book. Okay. All right. Now another thing that I pointed out when I brought up ArcMap is that some of the attributes, some of the data side, it can be qualitative and some of it can be quantitative. Oftentimes, a feature can have both types of attributes. Okay? And we showed that before. A state can have a name. That's a qualitative attribute. It's just a label. It can also have a quantitative attribute like population. Then to make things to blur that line even further, you can have a quantitative attribute that you choose to symbolize in a little bit less than quantitative way. For example, let's say that I wanted to symbolize the states of the United States of America by their populations, but I just wanted to do high, medium, and low. Do something like that. Technically, that's referred to as ordinal, which we'll talk about here in a second. Okay. Now, so far, when we've talked about points, lines, and polygons, we are conveniently making the world out to being discrete. In other words, a polygon has a boundary, and that boundary tells you whether you're inside or outside the polygon. Okay? Is there anywhere where you're almost in Mississippi? Well, you could say, yeah, I guess you could say you're almost in Mississippi if you're just outside of the state. But I should say it this way. You're either in Mississippi or you're out of Mississippi. Okay? You're either in Lamar County or you're out of Lamar County. You can be close to Lamar County, but that's what I mean by discrete. Okay? There are some spatial data that are not that discrete. For example, when I'm talking about elevation, what's the elevation at a particular location? Would it be easy to symbolize that with a polygon? No, because the value of elevation is constantly changing. So it's continuous. Temperature is another continuous variable. Now, we can choose to symbolize it as discrete. In other words, you can say, okay, in all this area, it's between 10 degrees and 20 degrees. And in all this area, it's between 20 degrees and 30 degrees, and so on. Okay. But in general, we can think of the world as having both discrete and continuous entities. All right. Also, our quantitative attributes can be divided up further as to whether or not they are in totals or whether or not it's derived. And this will actually play out a lot over the next few weeks in which map types we can use. Okay? Totals are values that represent a count of some entity. So population is a total. Okay? That number represents the total population of that state. Is another way to say it. Now, if I had another column that said cows, that would also be a total. Or if I had one that said the number of births in Mississippi, okay, that's another total. Just anytime I could say, if you could put the word total in front of it, it would still make sense. Like the total number of births, that would be a total. Okay. Now that's in contrast to derived data. Derived data means that you've taken the data and manipulated it, usually with another attribute, so that it is normalized. And one example of that is a statistic like that we often map, actually, population density, which is people divided by area. Okay? So we could have it be spatially referenced like that, people divided by area, or cows divided by area, or live births divided by area, or anything like that. Okay? We could also divide it by another attribute that's not the spatial data. So we could make a attribute that is, let's do births. The number of births per person. How is that information different than just the number of births? What makes that a little bit different? What does the number of births per person tell us that just the number of births does not tell us?
Percentage?
It's kind of like a percentage. We have to manipulate it a little bit more to get it to be percentage, but it's at least a rate, right? So it's like a birth rate. Okay. So if we had 5 births per person, that would be a lot, especially if it was also, again, per year or something like that, right? So the total number of births, the total number of people, get a number of 5, we could say, whoa, they're having a lot. That's really not possible, right, per year. But maybe it's over a lifetime, 5 births per lifetime. We have one country that has 5 births per lifetime and another country that has 2 births per person per lifetime. And you could say, well, okay, that country has a lower birth rate. What other assumption would you be able to make? I know this isn't a human geography course, but what's different about the country that has 2 and the country that has 5? The population is changing differently in both of those places, right? How's the population changing relative one versus the other? Okay, so that's taking it a step further than I thought. That's great. One's probably a third world country. One's probably more industrialized. Okay, yes, in a human geography course, you'd learn concepts like that. But at least you could say, even if you hadn't taken a course or you didn't learn that principle, at least you could say that the first example where it's 5, that population is growing much more rapidly than the country that's only with two births per lifetime. Okay, it would be an interesting map, right? You can make a map of all those places and see if it correlated, or you can make another map of income or something like that and see if it did in fact correlate with GDP, with being a third world country and whatnot. All right, that's what we're talking about. So almost everything that we can put on a map, you can think about in terms of these trade-offs. So if I've got a mine, and I just choose to symbolize it, like you've probably seen mine symbols on maps, as a crossed pickaxe and shovel, that would be a qualitative symbol for a mine. I could also have a bunch of mines on my map. Instead of showing them all as just mines, I could change the symbol so that the symbol got bigger as there were more coal. So one map might be very appropriate for just showing, hey, look at all these mines in this area. Okay, another map, if I wanted to actually see the more productive mines in my area, change the symbol as to how many tons of coal it generated a year. And by the way, tons of coal would be a total, not derived. All right, airport. I could just show an airport, or I could show the number of aircraft that left that airport that year. Again, probably as a symbol, as a point. River. Okay, I could choose to just show all rivers as blue lines, or I could choose to symbolize those rivers by their volume of water. Maybe I would change the width of the line. Forests. Forests would be polygons, and probably most often You've probably seen maps where forests are just big green polygons. Well, what if I changed them to be the darker the green color, the more board feet of timber were generated from that particular forest, and so on. I won't go down through all. All right, the spatial view is this discrete versus continuous. Okay. I could have a map where I had a bunch of points, and I showed what the temperature was at those point locations. Okay. Temperature at your home, or something that's more often done is that most airports have weather stations and record the temperature. So I could have a point at every single airport location, and the point could be colored as to how warm the temperature was. Blue for cold temperatures, yellow for medium, and red for hot. Okay? Or I could have a continuous map that showed the temperature everywhere. It'd be more like a surface. And precipitation, elevation, those are both the same way. Okay? So these entities that exist in the real world are continuous, but we could symbolize them in a discrete manner at known locations or in a continuous manner across the entire surface. Okay. And then I've already given a lot of examples: total population versus people per square mile, employment in mining versus mining employment as a percentage of all employment. Okay. Sometimes we're going to make maps and we're going to be mapping totals. There are maps that are more appropriate, map types that are more appropriate for totals, and there are map types that are more appropriate for derived data. And that's one thing that we'll cover over the next 4 or 5 weeks when we talk about different map types. Okay, we talked about quantitative versus qualitative data, and I'm going to break that up a little bit more. Okay? Nominal is qualitative. It's kind of like a stream here. Qualitative and nominal pretty much mean the same thing. And then I'm going to move this way, and we're going to get more and more towards true quantitative data. So the first step towards quantitative data is to just have labels that indicate the position on a quantitative scale. So in other words, if I map income, but instead of showing actual values, I show high, medium, and low, that would be an ordinal scale, okay, ranks or orders. If you are looking at a map, you can tell that it's ordinal if there's no way to really use math to explain how high or how low something is. You just know that it's higher or lower than another area. Okay, that's how you can tell it's ordinal. So if you can look at a map and there's a legend that tells you that this population earns twice as much as this population, that's still quantitative. It gets into this interval or ratio data. However, if you just say, okay, this is a high income area, this is a low income area, that's ordinal. Because you don't know, do they make twice as much or 3 times as much? Ordinal data, ranks or orders. Okay, and then interval means that it's fully quantitative data, means it's using numbers, but it's scaled with an arbitrary 0. And this distinction is a little bit important when we go try to make derived data. So if it's scaled with an arbitrary 0 value, like temperature, it's not usually possible to make a ratio out of that data, particularly like with other data sets. So you don't have temperature per population or temperature per area. I mean, there's some cases where it does make sense, but it's got an arbitrary 0. What do I mean by arbitrary 0? Does anybody know what 0 means in temperature? Like what, on the Fahrenheit scale, what is 0? Exactly. It's the coldest temperature that he'd experienced in his lab. Okay, so that was 0. That's really arbitrary, right? Because what if he'd been somewhere colder or somewhere warmer, he would add a different 0. And what's 0 on the centigrade scale? What's that? Freezing. What freezing point for water? Exactly. The freezing point for water. Now, you could argue that's a little less arbitrary, but it's just something that they picked. I mean, there's so many other liquids out there, and why not pick one of those? But it's arbitrary. Another way to think about it that may be a little bit easier is that does 0 represent the absence of the thing that's trying to be measured? So does 0 represent the absence of temperature? No, it doesn't. Okay. Now you could argue that like Kelvin, but I've never seen a map of temperature in Kelvin, is the absence of temperature, but it's really the absence of molecular movement, right? I'm not a physicist, but temperature is, it's related to that concept. But that's one way that might help you. So with precipitation, though, the example on ratio, 0 really does mean the absence of precipitation. There was no precipitation. Or 0 population means there's nobody there. Elevation, every year I say I probably should have put that up with interval, but because 0, what's the absence of elevation? It's more like temperature. So that's an error. I should move that up there. Okay, so precipitation, population, things like that. Those really are ratio level data. Okay? Nominal, ordinal, interval, ratio. And one thing that's tricky is that sometimes, because we're using computers, okay, look at this value right here. If I open up the attribute table again, this thing that's called state FIPS. Okay, state SIPS, is that a number? Yeah, it's a number. We all know 15s are numbers, 30s a number, 25s a number. Those are numbers. But the thing is, that attribute is not not ordinal or interval ratio. Those numbers are basically just codes that the government uses because sometimes it's easier to tell a computer to use a number than a name, particularly. So those are unique identifiers for states. So for all intents and purposes, that is ordinal data. The state FIPS code. Sorry, not ordinal. Nominal data. It's labeled. Okay, 15 equals Hawaii. They're the same thing. 53. 53 equals Washington. You're probably thinking, why are there 53 if these represent states? There's goes all the way up to 56. I know that DC has its own FIPS code, but maybe some of the territories do too. Anyway, those numbers represent states. So each one has a different code. Yeah, there's DC. It's number 11. And so Pennsylvania jumps all the way to Rhode Island. So my guess is that although Puerto Rico is not on this map, it's one of the P's that's left out there. And I don't know what the other P is, but you can see it jumps from 42 to 44. And then, not that this even matters. WTV. Yeah, you can see Virginia jumps from Virginia to Washington. My guess is 52 is Virgin Islands, and so on. Anyway, so it probably includes territories, even though it says state FIPS. Okay, back to this. Yeah, and your attributes themselves can be discrete versus continuous, but usually discrete means nominal. And then as you go this way, you get more continuous. Interval ratio or continuous data. Ordinal is is kind of the middle ground. All right, when we do this process of converting from larger scale data to smaller scale data, we oftentimes do things like simplify the geometry or the shape, the where information. So we take something that was lots of polygons and might make it a single polygon. If it gets even smaller, we might just symbolize this as a point. So these might represent neighborhoods. Okay? We aggregate some of the neighborhoods at this level. We aggregate it to the entire city level here. We might symbolize it as a point later. Okay? Now, if it's already aggregated, we can't really break apart its aggregation levels. So you just see it as a smaller or larger. You can simplify it, though, even if you can't re-aggregate it. All right, so this is what I talked about at the beginning of the lecture. In fact, this table is very similar. It's just older. It shows 1990 data. So this is some total derived data. We've got some attribute values that represent some totals and some derived data. All right, this is a clip from your book, and this basically just talks about the different types of view. So we got our characteristic view, our measurement level, our spatial view, and this is all a single row in the textbook. Okay, and you don't need to memorize this chart or anything. This chart is a fancy way of telling you what's coming up. So we're going to talk next week, for example, about choropleth maps. That's in chapter 6. Okay, choropleth maps map two-dimensional or area data. Okay, typically choropleth maps are for mapping derived data, not for mapping totals. That's the way you read this. So we're mapping derived data, not for mapping totals. It's hard to put this up here, but let's see. We're 1, 2, 3, 4, 5, 6, 7 up from the bottom. So we're on this row. And so choropleth maps are discrete. In other words, we're mapping things with discrete boundaries, like states. In fact, when I made the map of population, that was another choropleth map. We can map interval ratio or ordinal data with a choropleth map, but not nominal data. Okay, nominal data isn't considered a choropleth map. That's just mapping. That's just coloring it in by a unique value. And then it's quantitative data rather than qualitative data. The data itself, the characteristics of the data. So this map will make a little bit more sense as we process through each week. What we're going to do each week is cover another one of these: choropleth, dot density, proportional point symbol, surface, cartograms, and so on. And then this kind of covers base maps, the general purpose base maps. General purpose base maps can have points, lines, or polygons. It's usually discrete data. In other words, we're just showing roads and streams and things like that. That's what's in the background. It's not typically necessary to show quantities. The quantities are the things that we put in our thematic maps, not in our base maps. Usually qualitative data. If you look at Google Maps, which is a good example of a reference or a base map, we can see lots of symbols on there, but very few of them are telling us about quantities. You could argue that interstates carry more people than roads, than city roads and stuff like that. But for the most part, it's just labeling it as an interstate. Okay, now, once we do start talking about this stuff, we're going to talk about how to communicate our quantitative data out to the end user, to the map reader. And one of those things that we can do is adjust these visual variables. These are the things that we can do to the symbols to make them different or to communicate to the user a difference in quantity or a difference in quality. One thing that we can do is adjust the size of our symbols. Basically, we make them bigger or smaller. So when I made that point map of the United States, the bigger points represented more population and the smaller points represented smaller population. So size is a visual variable that we can modify. Right? That's pretty straightforward. Shape. Shape is not as straightforward because oftentimes if we want to modify the shape of an object, we're messing with its spatial properties. And there actually is a map type that we'll discuss called a cartogram where we do mess with the shape a bit in order to make a point. But it's one of the reasons why we call it a cartogram is because it's almost not a map at that point. We're distorting the true shape of that object. However, that's not the only way to communicate using shape. What if we take a point symbol, a symbol that doesn't have an area to begin with, okay, an entity that doesn't have an area to begin with, and we change the shape in order to represent something. So an example would be putting a tree shape on the map to represent a tree, even if it doesn't actually look exactly like the tree, right? So, you know, yeah, this is what I mean. Okay, these these aren't, I can add the cities in here. So I'm going to add the cities in here, right? So here's all the cities in the United States, and I can change the symbol to something like, like this. I guess that didn't really change the shape, more of a star or something. But if I did make them stars, it kind of communicates to people that they're probably capitals. And so let's do that. So if I open the attribute table here, I've got a column probably that says capital, yep. So I'm going to sort this. So I've got all these state capitals. There we go. All right, so I'm going to go to categories, and I'm going to go to capital, not all values, and I'm going to make the national capital green star, make all the state capitals black stars, and make all the rest of the places small dots. All right, so now, it's a horrible map, but I've used shape to distinguish between regular cities as circles and cities that are capitals as stars. So that's another example besides the use of a tree. Oh, it's on there. Use of a star for a capital. Okay, so here's some other visual variables. Oops, went too far. Orientation. So this happens with things like labels. Okay, if you write your label, your word for a particular thing, it implies that there's either flow or when you travel along that street, you go in that direction. So it can communicate actual real-world characteristics. Texture. Texture is something that we can change on a map. A polygon can have texture. A marsh, for example, often has like this little hash pattern that looks a little bit like grass growing. Okay? Oftentimes it's used as an overlay value. All right, saturation and value are two modifications of the color that we can change. So saturation is basically how saturated. I can't say that, but if you think about a fire engine and a radish, they're different colors, but they're almost the same darkness. One has less gray in it, basically. So that's the difference between that's saturation. How saturated is how much color is showing, or the value itself, which means how light or how dark it is. All right, here are some examples. So here's changing the value. The lines between these lines, there's a difference in value, okay, in terms of the shading. Okay? So this one's shaded darker than this. Here's some differences in pattern and texture: marsh, sand, forest. Here's some differences in width to show how much flow is occurring along different areas. Here's some difference in width just to show differences in different types of lines. This is all qualitative in nature. This would be quantitative in nature. Then here are a few more examples of things that you can change. With points, you can make the size larger and smaller. Lines, you can make them larger and smaller. With areas, it's kind of hard to make them larger and smaller, except for that special case of a cartogram, which we will talk about. Value is changing basically the lightness. Okay. All right, this is a black and white diagram, but hue is changing the color. So changing the hue is one thing that we can do. We can do that with points, lines, and polygons. We can change the lightness value. We can change the saturation of points, lines, and polygons. We can change the orientation of points. It's harder to change the orientation of lines and areas. Shapes, we can change the shapes of points. We can change the shapes of lines. We can basically symbolize them as different shapes. With areas, we're actually kind of really changing the texture. There's not too much of a difference between these. We're changing the pattern that's being displayed on top of the areas. Arrangement is basically the symbol type. Change the symbol type. Change the symbol type for lines and areas. Okay, texture, we already talked about that. Focus, you could make a map where certain things were out of focus and certain things were in focus. That's not commonly done, though. All right, we're going to talk a little bit about errors in cartography. So our data often drives what type of errors that we'll see. That's why we're introducing it in this lecture. That's what we're talking about in this lecture. So one of the errors that can occur they're referred to as source errors. Okay? Most of the time as cartographers, we derive data or we get data that somebody else has created initially. Whether or not that means that they actually have created a GIS file for us to use, or they've handed us a bunch of coordinates. In either case, there could be errors in that data. Okay? So if it's an existing map, it could be originally meant at a different scale. And so the level of detail is not there in the data that we want to use. It could be in a different projection. And depending on what projection it is, there could be some error associated with converting from one projection to another. It could also be a map, the data itself could be from a previous time period that is no longer accurate because things have changed over time. So these are all errors that come from your source map or your source data error. So you need to think about those. Go through these pretty quick. If you enter your own data, you create your own data, which we will do, and I know you do that in the GIS lab. Create your own data. You yourself can make an error. You can make an error in the digitizing of a boundary. You could also make an error in the attributes themselves if you're entering the values yourself. So we've got attribute error and we've got coordinate error, basically. If you go to process the data yourself, if you're calculating, for example, population density, you could make an error in processing. You could use a wrong formula. Okay? With population density, it's pretty easy because it's just people divided by area. But let's say you're trying to do growth rate, and you took, population A and population B, time period A and time period B. You need to be careful about which one you're subtracting from which one to get a positive growth rate. And of course, numerical rounding, data classification, which we'll talk about a lot next week when we talk about Choropleth maps. All right. And then one more source of error that people don't often think about is the error that happens because your map reader doesn't understand your map. In other words, you're trying to present story A and number A, and they read it wrong. They look at the map and they see it wrong. And these errors come about because of design. So maybe you choose the wrong thematic map type. It doesn't communicate what you want effectively. Or you choose the wrong scale, the wrong projection. You generalize too much or too little. You choose the wrong symbols that they can't understand or can't read. Or you use color that's inappropriate or that can't be read or understood correctly. All right. Now, I've said that as cartographers, often we use data that already exists. Where do we get that data? Right, there are lots of sources for that. The data that I just downloaded and showed you at the beginning of class, the population data, it came from the U.S. Census Bureau. Okay? U.S. Census Bureau has a lot of data, and it's not just population data. They also have that other information where we had ages separated out. They also have some housing data. How many people are renting versus how many are owning. They also separate out things like race and income and educational attainment. Now, they don't send those questions out to every single person. So that data is aggregated at different levels. In other words, you're not going to get race, income, educational attainment at what we call the block level. In other words, a census block is a defined area on the ground. You don't know what census block you're in, but a block in the city is roughly analogous to an actual block. Okay? But when you go to get census data, you're only going to get the number of people in a block. You're not going to get all the detailed information. First of all, they don't want to give that out for privacy concerns. And secondly, it's not always a good representation because not everybody receives the longer form that asks all that information. So you typically, the data besides just population starts becoming available at the block group level, and there's even more at the tract level. And a block is, like I said, in the city, it's an area like a city block. But it usually has about 100 people or so, and they can vary widely. So don't take that number as gospel. But a block is a block group is about 4 or 5 blocks. And a tract is a number of block groups. And then we all know what counties are. County subdivisions are just pieces of counties. Urban areas, congressional districts. There's actually many more. One of them, you've probably actually heard of the term metropolitan statistical area or cosmopolitan statistical area. Sometimes they abbreviate MSA or CSA, and they'll say, oh, I'll pick a city. The St. Louis MSA has this many people in it. Well, the MSA is the area that surrounds, the urban area that surrounds St. Louis in that case. So just divisions that the census produces. So you can make maps of those divisions with census data. There's also a lot of data that the USGS puts out. A lot of it is more for background data, for base map data. They produce vector data. They also produce some raster data that you can just put in the back of your map. This is less common now that we have so many web maps out there. But they are a source of data. Here are some data sources for our state. Okay, the institutions of higher learning. That's the state board that runs the colleges and universities here, the public colleges and universities here in the state of Mississippi. They have an organization that they refer to as MERIS. It stands for Mississippi Automated Research or Resource Information System, but that doesn't really mean anything that it actually does. They basically handle a lot of the GIS data for the state. That's what their job is. And they also handle making sure that we all have licenses to ArcGIS software and the remote sensing software. But they do have a data download page. You can get good data for our state there. The Mississippi Geospatial Clearinghouse is another place to get data for our state. And that is run by the state government, which technically IHL is part of the state government as well. But that's the official state government world. Neighboring states, we've got Louisiana here, LSU, this is the equivalent of Marist in Louisiana. Then we've got some national and private. This URLs, use arcgis.org now. Okay. I already introduced this concept, but this is just driving home the point that these codes, these FIPS codes, even though they're numbers, are really codes for labels. So we've got state FIPS codes, which I showed you in the attribute table before. And we've also got county FIPS codes. Okay, county FIPS codes for counties. There are zip codes for zip codes, and those are also numbers, but they don't really mean anything. In other words, you can't say what's 39475 plus 39402, and those are just two different places. Just to give you an idea of how many of these units there are throughout the country. Okay, there are 50 states. There are 3,219 county level units. Okay, in Louisiana, our neighbor over there, and also I think Alaska, all their counties. Alaska they call them boroughs. Next door they call them parishes. But there are 3,000. What's that?
Boroughs, like
Pretty sure that's what they call them in Alaska. Yeah. And in New York, there are a few counties that are referred to as boroughs, but they're parts of a city. So New York has 5 boroughs. They're all individually counties on paper, but they're all part of the city of New York. Anyway, but I'm pretty sure all of Alaska's counties are referred to as boroughs. Yeah, it says right there.
Yeah, I didn't see that part.
So Louisiana, they're parishes. Alaska, the boroughs. Texas has 254 counties. It's a lot of counties. Delaware has 3. Counties are often a good, like for a map of the entire United States, counties are kind of like the smallest unit that you want to do for the whole USA. See here, I can go, oops. can add the county data. So now I have counties instead of cities. And the counties are small enough, but not too small, that I can do something like do another Chloropuff map, which will. So here's the population per square mile of counties in the United States. I'm going to turn off the interstates. Okay. Now, next week we'll talk a lot. Oh, sorry. Exiting the slideshow is. Okay, that's what I was talking about. So this is a Chloropuff map of the United States showing population by county. Okay, that's not very interesting, right? Until I change the classification system, which we'll learn a little bit next week. I'm going to change this to quantile. Now I get a little bit more interesting map where you can see the more populated. This is population per square mile. You can see more populated area, less populated area. And on the west, basically, along the Front Range, on the Wasatch Front. Here we've got the Boise, Napa area. Okay. All right. Okay. In order to get to that next week, we got a few more things to talk about here. Yep. Okay. So one of the things, and we can go through this pretty quick because we've already mentioned a bit of this. Our data sets, when we display them, we can make ratio data by dividing one variable by another variable. That's population data. Okay. We can also make a proportion, which is dividing one variable by the total of that variable for all items. In other words, if you did that with population, the difference here would be, this would be dividing population by density, or it would be dividing population by area, or population by some other variable. Here, we're saying, okay, divide population of Mississippi by the total population for the entire United States. And so then you're making a map of the proportion of the population of the United States that's in Mississippi. So Mississippi's value becomes probably something like less than 10%, right? Maybe even, well, way less than 10%, probably less than 1% of the United States population is in Mississippi, I would imagine, because that's probably right? What's the population in Mississippi? I think it's around 3 or 4 million. Is that correct? What's that?
I think it's like 2.9.
Oh, 2.9, okay. Yeah, so it's less than 1%, because the population in the United States is approaching 400 million. So you have a value of less than 1%. A percent, it's the same as above, but it's the same as any of these, but you multiply it by 100 to make a percentage. See what I'm saying? If you don't multiply it by 100, it's still a proportion. You multiply it by 100 to get a percentage. So the difference between that is, if I say that 0.01%, sorry, if I say 0.01, in other words, if the proportion of people that live in Mississippi is 0.01, then it's 1%. Okay? And then multiply it by 100, move the decimal place over 2, and get the percent. Okay? It's just how many people out of 100 live there instead of the proportion, which is the number, the raw value. Okay? So another way to think about that is if there were 10 questions on a test and you missed 4 of those questions, that means that you've got 0.6 questions correct or 60%. All right, rate is the same as percentage, but we're going to use a different multiplier instead of 1,000. Sometimes, 100. Sometimes we're going to use 1,000. So the birth rate is often expressed in the number of live births per 1,000. Why? Well, it's just an easier number to think of. It makes the number come above 1. So you get like 1.23 instead of, if it was a percent, it would be like 0.2 whatever. It'd be a smaller number. So a rate is just used to make a proportion into a number that's easier to think about. Per 1,000 or per million. Okay. All right. So all of those types of things we might be putting on maps, or we will be putting on maps. All right. Here's just a few examples of different things that we could make maps of. All right. Last thing that we need to talk about before next week, when we start talking about classification schemes, is that we need to review really quickly some statistical terms. Now, you may have learned about these in high school, and that's great. It'd be great to get some feedback to make sure that that you understand them when I go through them. All right. So we can take a bunch of numbers. For example, if these represented the population values in the United States, and a bunch of population values, we can come up with the average value in a few different ways. And we call that average value measures of central tendency. Okay. All right, so the most common one that we usually think about is the mean. Right? What's the mean? How do we calculate the mean in simple math terms? The mean, the average population value would be, well, how do I calculate the average test score in a class? Yes, add them all up and divide by the number of observations. So calculating the average population in the states, I would take all the populations for every state, add them all up and divide them by 50, because there's 50 states in the United States, and I come up with a number. That's mean, okay? That's the mean. Another thing I could do is, let's say I had all of the counties in Mississippi, and I wanted to find out what the average population in each county was. I could add them all up, divide by the total number. All right, median is a little different, okay? But it's also a measure of central tendency. Does anybody know what median is? The middle, yeah, it's the value in the center of the distribution. So if I took all the values and arranged them from the lowest to the highest, the median is the one in the middle. Okay. Another word for it is the value that's at the 50th percentile. Right? The number right in the middle. Now, sometimes people say, well, what if there's like an even number of values? What if there are 4 values? What's the median? Typically, the convention is to use the average of the 2 middle values. Okay, so the average of the second and third value would be the median in that case. All right, there is another one that I'll have on here. Another measure of central tendency is the mode. And the mode is the most often repeated value. Okay, so that's another one. I think I have that on a different slide. All right, an outlier is a value that is different, significantly different from all of the other values. So in our state, I don't know if there are any, but maybe there's a county that has a much higher or much lower population than the main group of counties. Who knows? But that's what an outlier would be. If there was a county that dominated, in other words, it had like 2 or 3 times the population of any other county, that would be an outlier. The reason we talk about that is that oftentimes we'll have to symbolize those differently when we make maps. They'll influence, well, an outlier will affect the range in a strange way. Because what's the range? It's not a trick question. The range is just the highest minus the lowest value. So if the lowest value for population in our state was 800. I don't know if there's a county that only had 800 people. And the highest was 300,000. Then the range would be 300,000 minus 800. So it would be 200,000. 200,200 would be the, or would be 299,200. That's what the range would be. All right. These are also these are measures of spread. Okay. So the variance is the average squared difference from the mean. So what does that mean? Well, if you took all the values and you found out what the mean was first, and then you took every value and you subtracted that value from the mean, and then squared it, and then took the average of all those values, that would be the variance. It kind of tells you what the average distance away from the mean is of all the points. The reason that the formula uses, there's actually a number of reasons the formula uses the squared difference. One is so that they'll all be positive. All right, so the standard deviation is just the square root of the variance. So the standard deviation is in the same units. If you get a standard deviation of, for population, if you get a standard deviation of 700, what that's saying is the standard deviation is 700 people. Okay? So the average number of people in the counties might be, I don't know, probably 10,000. And then if you get a standard deviation of 7,000, what that means, I'm sorry, 700, what that means is that most of the counties are somewhere between 10,700 and whatever 10,000 minus 700 is. I say most, it can be defined in a few different ways. And this is just calculating out standard deviation. You don't need to calculate a standard deviation for the test or anything. Okay? But this is what I mean by most. Okay? Lots of distributions, in other words, maybe, I don't know if it's like this, but if we're talking about the number of people in each county, okay? If these are all the counties, most counties might have about 10,000 people in them, but some have a lot more and some have a lot less. Okay? Now, if they really are distributed like this nice bell-shaped curve, this is called a normal distribution. Normal distribution means that there's a defined way that this rises and falls. So this is the mean. These are the places that have less than the mean. These are the ones that have more than the mean. This is the frequency. In other words, the number of counties. So lots of counties, like maybe 50% of the counties, have a value very close to 10,000. Some of them don't. Some of them have higher. Okay? Most populations that actually exist out there don't look exactly like this, but there are a lot that are close. And more often in nature, they're closer than things that that aren't natural. So, for example, the height of, like if I just had the height of men in the United States, it would be pretty close to this normal distribution. However, things like income aren't distributed like this. In other words, there's not a big bell in the center, and just a few people make a little bit, and a few people make a lot. Okay? How do you think the income looks like in the United States? I mean, it is more like this than it is in some of the other areas in the world. But which way do you think this big blob would go? Well, actually, or you could just say which tail would be big. If you think about income in the United States, or really income anywhere, but in the United States. So there is a floor for income, right? I mean, you can't make less than 0, right? But is there any ceiling, theoretical ceiling for income per year? No, there's not. So this tail goes out a long way this way. Okay? And then there is a middle class, and then there's there's poor. There's less people in there than there are in the middle class, but even the middle class, you can think of it as divided. All right, I'm trying to think of, there's probably other populations that are bimodal. In other words, there's people down here, and there's a little bump up here. Okay? That happens in, well, if I were to make the mistake of saying, okay, what's everybody's height, but I'm going to mix men and women on the same chart, it would be bimodal, just the height of people in general. It'd be bimodal because there'd be a bump where all the females' heights, and then there'd be another bump where the average male height was. Okay. So there'd be two bumps on that chart. And so this is a normal distribution where the mean, median, and mode are all the same. In a skewed distribution, if it's skewed in the positive direction, like income, the mean will be skewed toward the direction that the longer tail is. The median will only be slightly offset, and it's possible for the mode to be almost the same. In other words, the most often repeated value. It's possible. Again, if it's skewed in the negative direction, the mean will go that way, the median will be less affected, and the mode will be the least affected. Okay, so what does this mean for our maps? Well, sometimes we may want to show median values, and sometimes we might want to show mean values on a map. I'm going to skip this next one. It's talking about how peaked the distribution is. It's not important really for most of the maps that we'll make. All right, and then this is where I'm going to stop. I'm going to wrap this part of the lecture in with the Coropath mapping lecture, okay? Because we're gonna start talking about classification schemes, and all the examples are mostly Coropath maps. So we'll talk about this next week, all right? And the lab doesn't have anything to do with this part of it. I put it in this lecture each year in case I get that far, but I never do. So we always end up talking about it next time. All right, so I'm going to pick it up on 32. All right, so like I said, the lecture usually ends around 2:40, which is exactly what, well, not exactly, but close to what time it is. I'm going to go ahead and stop this broadcast, and I'll create another one just for the lab, and just give me about 10 minutes to rest, and then I'll introduce the lab. Just rest my voice. And I'll introduce the lab. The lab today is like the labs from the last few weeks. It's pretty straightforward. So if you want to get started on it right now, that's fine. But I'm going to get a drink, and I'll be back in about 10 minutes. Anybody have questions about what was presented today? Sarah. No, you don't have to stay. Nope. You're not necessarily. You're not bound to stay here. You know, if you look over the lab and you think you can get by without any questions, of course. Yep. All right. Thanks. Any other questions? I'm gonna stop the broadcast.